quickly discuss a couple of more definitions in thermodynamics and then close off.
Yes, sir.
So, enthalpy change is what we were discussing yesterday. Now, there are a few more enthalpy changes which you need to understand here. Now, I think I discussed up to bond enthalpy, bond energy also yesterday, correct?
Yes, sir.
The bond enthalpy is the energy needed to break the bonds. Let me just quickly define bond energy as well. Bond energy energy released when bonds are formed. That's the idea. So when a particular type of bond is formed, the amount of energy which is going to be released is basically going to be your bond energy there. Of course, average energy per mole type is what you calculate. Now, so if I'm going to be looking at enthalpy of reaction, we have discussed this from the point of view of what to say enthalpy of formation earlier and enthalpy of combustion earlier. Let's recap that part again. So from the point of view of enthalpy of formation, how do you write it? Sigma of what? Enthalpy of formation is defined for what? Products or for reactants?
Formation. Products.
Products. So what should this become? This will
Sigma
become
products minus sigma reactants.
good. So it will be products minus sigma of reactants. Right. Next up. If I'm going to be having the same enthalpy of reaction,
Combustion.
considered from combustion point of view. Combustion is defined for what? Which side?
Reactants.
Reactants.
One.
So it will be enthalpy of combustion of reactants minus
Products.
now. Let's now go for bond enthalpy if it is given. Remember, all of these kinds of methodologies or these formulas or these kind of direct approaches are only applicable if all the values of enthalpy of formation are given for reactants and products, or if all the enthalpy of combustion values are given for reactants and products.
Yeah.
If we are not having all of them, if we are having some enthalpy of combustion, some enthalpy of formation, some bond enthalpy, some other stuff all mixed together,
Clear the
no
reactions.
shortcuts. No shortcuts. You'll have to actually do addition and subtraction. You'll have to write the equations, do addition and subtraction, and solve it.
Yeah.
You understand the proper process here?
Yes, sir.
Now, next up. If I'm given bond enthalpies of all the different types of bonds, bond enthalpy is for breaking a bond.
Yeah.
Now, if I consider a reaction happening, reactants are becoming products. In which side do I break the bonds during the reaction?
Reactant side.
Reactants, we break the bonds. Products, the bonds are going to be formed, correct?
Yes, sir.
So, when you are given bond enthalpies for breaking the bond, right? What should it be then? Is it defined for reactants or is it defined for products?
Reactants.
Reactants. So I'll have it as sigma of bond enthalpies of the reactants minus sigma of the products. You understand the idea here?
Yes, sir.
So the principle is going to be the same, but you can extend it beyond that. Now, a couple of more definitions. Now, the next definition has to do with neutralization. So when it comes to enthalpy of neutralization, this enthalpy of neutralization, let's quickly try to go back to what is a neutralization. If I have, say, HCl neutralizing with NaOH and say HNO3 neutralizing with NaOH, what is happening? We are going to be having these two will react with each other, these two will also react with each other. Reaction will give me NaCl, but the NaCl is not existing as NaCl really, right? It is actually going to be
Yes.
existing as what? Na plus
Oh, yeah.
plus Cl minus. Both are spectators.
Hmm.
Same way here, I'll have it as Na plus plus NO3 minus. Both are
Yeah.
spectators as well,
Yes, sir.
right? And I'll be having H2O as the product, other than these two,
Hmm.
right? So effectively speaking, on the reactant side, how are they existing in each of these cases? Here
Aqueous.
also it is existing as H plus
Oh,
plus
right.
Cl minus plus
Hmm.
Na plus plus OH minus,
Hmm. They rearrange it.
correct?
Yeah.
So technically speaking, I can say that this Cl minus and the Na plus are existing on both sides.
Yes.
They're not really doing much there. They are
Hmm.
spectators in
Hmm.
reactant side and spectators in products also.
Yeah.
Same thing applies for my Na plus and NO3 minus as well.
Hmm. Yeah.
So if I am having a strong acid, strong base neutralization, the idea here is very simple. The real neutralization reaction is only going to be H plus plus OH minus giving H2O. As simple as that.
Hmm. Okay. Yeah.
So when you're going to be having H plus plus OH minus giving H2O here, that is going to be something which is going to be involving a standard value every time. Let me just get the value out here. So the value seems to be some particular value in kilojoules per mole, but I would prefer it to be in multiple units there. Let me get you different units as well. Okay. The value seems to be minus 57.3 in kilojoules per mole. That is, this is supposed to be minus 57.3 in kilojoules per mole. I'll just calculate that more exactly because I'm seeing a lot of shitty values here online. You'll have to find the proper value. Yeah, so the value is around minus 57 to minus 58 kilojoules per mole. Minus 57.4 is acceptable then. Okay.
Yeah.
Minus 57.9 is also available here. Chalo, whatever. So minus 57 point something, say 4 kilojoules per mole. It doesn't matter what the exact value is. You check your NCRT textbook and go with that value. Okay.
Hmm.
Well, I'm able to find too many values here online stupidly. I'll have to get a proper book and check this shit out as well.
Hmm.
There is a value. It doesn't make a difference what the number is going to be. Now, this is going to be something which you'll have to remember in other units also. I would recommend you remember this in kilocalories as well. So how do you convert it to kilocalories? You divide this sucker by 4.2.
4.2. Hmm.
Sure. Let's do that now.
3.2.
It's around 13.6,
13.6.
making it more exact, 13.7. That makes more sense. 13.7 is what I remember. So minus 13.7 kilocalories per mole. So for every 1 mole of H plus or for every 1 mole of OH minus which is neutralized, the value is going to be this. So if I'm asking you what is the enthalpy of neutralization for NaOH, the definition is going to be when you neutralize NaOH with sufficient amount of strong acid, how much energy is released, which is going to be this value.
So no matter what, it's always going to be constant.
Any
If you
strong
have
acid, any strong base, the value will be this. If it is going to be providing only one H
H
or
plus.
one OH minus.
Yeah.
If I ask for H2SO4,
Oh,
enthalpy of neutralization of H2SO4,
will
that gets
change again.
strong acid, but it provides 2H plus, correct?
Yes, sir.
What will that value be then? It will be double this value. I'll define enthalpy of neutralization now. Pay attention. So if I am looking at taking 1 mole of that acid or base, and if I'm neutralizing it with its corresponding opposite partner, strong fellow there. So if I take enthalpy of neutralization of HCl, how will I be defining it? I'll take 1 mole of HCl.
Reacted with strong base.
I will neutralize it with sufficient strong base
Hmm.
and then look at the enthalpy change in the process. That will be this value because HCl provides only 1 mole of H plus. Same thing will apply for NaOH also. But if I
Hmm.
take barium hydroxide, that guy
Hmm.
provides 2 moles of OH minus.
Yes.
So if I take 1 mole of barium hydroxide and I neutralize it with sufficient strong acid, I don't care which strong acid.
Hmm.
There are 2 moles of OH minus getting neutralized here, correct?
Yeah.
2 moles of OH minus are getting neutralized, I'll have twice the amount of energy being released.
But then 2 moles of H plus also with that.
Yes, I don't give a shit about how much H plus is going to be required. I'm only interested in how much of this reaction is happening. The idea here is very simple. For every 1 mole, look at the units I'm using here. For every 1 mole of the substance getting neutralized, I'm going to be having this much energy released.
Hmm.
So for 1 mole of H2O being produced from 1 mole of H plus and 1 mole of OH minus combining, I'm going to be getting this much energy released.
Yes, sir. Right.
If I took, say, H2SO4 in this case here, and I look at enthalpy of neutralization of H2SO4, when I put per mole there, I'm putting per mole of H2SO4 undergoing neutralization, not for H plus there.
Okay. 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 Got it. Yeah. Hmm.
You get the idea?
Yes,
If
sir. Yeah.
H2SO4 produces 2 moles of H plus, when it is undergoing complete neutralization with a strong base, it will necessarily require 2 moles of OH
2
minus.
moles of H minus. That'll be provided. Yeah. Hmm.
That is basically the idea there.
Yes.
Now,
Sir.
let's talk about what happens when there is a weak acid. If I take a weak acid like, say, HA, that guy does not dissociate completely.
Hmm.
So what happens is I need to force this guy to dissociate completely and then undergo neutralization.
Yeah.
So let's say the amount of energy required to dissociate this HA into H plus and A minus fully. If I take 1 mole of HA, I'm neutralizing 1 mole of HA. That is what
Hmm.
enthalpy neutralization tells me. But this time, since it's an acid, I'll neutralize it with a strong base.
Hmm.
So let's say the amount of energy required to break this HA, it has already broken down and maintained an equilibrium to H plus and A minus stage.
Hmm.
Yeah, let's say 10% is present like this. So 0.1 and 0.1. So this is left over as 0.9 at equilibrium.
Yeah.
Okay. Now I'm neutralizing this guy. Okay. So let us say to break HA into H plus and A minus, I'm going to be requiring, let's take a random value here, say 10 kilojoules per mole.
Hmm.
Okay.
Yeah.
In the equilibrium itself, it is already broken up to 10%.
Hmm.
but another zero point 0.9 is not broken.
Yeah.
So if I add a strong base, what will happen? That will consume this H plus.
Yes. Point one.
Correct. As it consumes this H plus, this reaction moving forward,
Yes.
more and forward,
Yeah.
which means as the neutralization happens, this dissociation is also going to be happening. The
Yes.
leftover dissociation, which is leftover, will happen.
Yeah.
Correct. That means how much of energy is going to be consumed for this dissociation now? Point 0.1 was already there. Point
Yeah.
0.9 was not dissociated.
Hmm.
This undissociated will have to break now.
Yes. Yeah.
So for 1 mole to completely dissociate, it required 10 kilojoules. So for
Mm-hmm.
0.9 to now dissociate, how much is going to be consumed?
9 kilos.
9. So I'll be having for leftover break to happen. I'll be requiring 0.9 moles to break, which
Yes.
in turn requires 9, or in this case here, 0.9
Into 10.
into the 10,
Hmm.
which works out as 9 kilojoules
Yeah.
absorbed. Where is this energy going to come from? Obviously from the neutralization.
Utilization. Yeah.
So how much energy is now going to be released as enthalpy of neutralization of this?
9 kilos.
9 kilojoules lesser than that. Think the H plus and OH minus are still combining, correct?
Yeah.
When they combine, when 1 mole of H plus and OH minus combine, this is the amount of energy released.
Yes.
That is still happening here also.
Yeah.
But
But
there's
then again 90 plus.
this extra shit is also breaking.
So we need to provide more energy.
Yes, you require a little bit more energy, or a little bit of the energy which is released is consumed away now.
Yeah. Okay. So we okay. Okay.
So it will
Okay.
release lesser energy.
Mm-hmm.
So my enthalpy of neutralization
Yeah.
for HA is going to be involving that minus 57.4, which is
Plus.
released for the H plus and OH minus to destroy, to
Hmm.
combine each other, plus the 9,
Plus the 9. Yeah.
because 9 is absorbed away, which works out as how much?
48. Minus 48.
You
Hmm.
understand the idea here?
Yes, sir. Yeah. Okay.
So based on the enthalpy of neutralization for a weak acid or for a weak base, we can actually back calculate and find out the alpha value for the weak acid or weak base. For instance,
Hmm.
if I gave the HA's value here as minus 48.4,
Yeah.
and I told you this breaking is going to be this much,
Hmm.
what can I conclude there? I can conclude that if this much energy is released, I should have had how much? I should have had this much. But I'm getting only, what to say, let me give you the same thing in a different way. So instead of giving it to you as minus 48.4, let's say minus 49.4 is released.
Hmm.
Okay. Instead of how much? Instead of a total of minus 57.4.
Yeah.
Now, how much has been consumed then? 8 has been consumed.
8 has gone to base.
8 has been consumed.
Hmm.
And let's say 10 kilojoules is going to be required to break 1 mole completely.
So 0.8 moles have to.
Zero point 0.8 moles are
So
left over.
equilibrium.
How
Okay,
much
like
is the
that you say.
alpha? 0.2.
So 0.2 moles. Okay.
So
Okay.
can you calculate the Ka
Um,
now?
oh yes. Yes.
You can, correct?
It's correct. Yeah.
You understand the idea here? So
Yes,
you
sir.
will be asked questions like that, connecting thermo and equilibrium.
Okay. Let's see. Hmm.
You understand the idea here?
Yes, sir. Yeah. Okay.
Clear to an extent?
Yes, sir.
Obviously, you'll have to put this shit down. I have not written it down over here. You'll have to explain this shit for yourself,
Yes, sir.
your own words. You
I'm
understood
done.
though, I suppose, yes?
Yes, sir. Yeah. For now. Yeah.
Now, you've learned a little bit of organic also.
Yes, sir.
Correct. So this is the connection between ionic and what to say, a little bit of a connection between ionic and thermo. Now there is other connections also. Let's say I'm going to be looking at say a carbon double bond carbon. I'm going to tell you that I'm going to convert it to a carbon single bond carbon. So what's happening really?
Bond breaking.
What is exactly happening?
Oh,
This is the reaction which is exactly happening.
oh yes.
So let's now consider the reaction a little bit more carefully and see what's exactly happened.
Hmm.
These are my reactant fellows.
Yes.
What are the bonds broken in the reactant side now?
Pi bond and then the HH
One
bond.
carbon, pi carbon, and one hydrogen,
And sigma.
sigma hydrogen. These are broken.
Hmm.
Correct? What
Yeah.
is formed here?
C sigma C.
No,
One C C.
sigma
No,
C
no.
was already existing.
Two. Two. Yeah, my bad. Two C. Two C sigma H.
Good. So 2C sigma H are formed in the process.
Yeah.
Right. So when you're going to be having this happening over here, you're breaking one carbon pi carbon, and you are technically breaking one hydrogen sigma hydrogen, and you're forming two carbon hydrogen sigmas.
Hmm.
Obviously, the two sigma bonds are more stable than the one sigma and one pi.
Yeah.
So this is going to be involving energy release. So energy is released in the process.
Hmm. Yeah.
Okay. So when energy is getting released in the process, now we can extrapolate this. Like for instance, if I'm converting benzene into cyclohexane, technically I'm breaking three carbon pi carbon and then converting it into this fashion here.
Yeah. Hmm.
Yes. So in that case, I should technically be having approximately three times this energy released. So if this is X, if let's say delta H for this reaction is going to be say minus X, then the expectation is that for this reaction, I should be having delta H expected
Minus 3x.
is going to be minus 3x,
But
right?
yeah.
But I will not get that.
Hmm.
Why will I not be getting that? Because this
Yes.
fellow is more stable than expected. Why is it more
Hmm.
stable than expected?
As
Resonance and
it.
what is it, aromaticity.
Yeah.
So the idea here is this. We assumed that they are all of similar levels of stability, but they are not
Yeah. Hmm.
because there is a resonance factor involved. So my expected value is minus 3x, but the actual value will be lesser than that. So let's take some numbers and then I'll give you directly that you'll understand better. So let's say this is minus 100. The
Hmm.
expected value is minus 300 then.
Yeah. But this will be like minus
On the other hand, will be like say
400.
minus 150.
Oh.
It will not be more negative, it will be less negative because the extra stability makes it less interested in destroying itself,
Yeah. Yeah. Correct. Correct. Hmm.
right? It is more stable. That means it does not want to break the pi bonds unnecessarily.
Ah. Yes. Makes
It is
sense.
more
Yeah.
reluctant to break its bonds.
Hmm.
So the actual value say minus 150. Then basically resonance energy
Hmm.
for benzene
Multiple.
that is going to be minus 150.
Mm-hmm.
Or let's change the numbers here
Plus.
slightly so that it is easier. This is unnecessarily complicating shit. Let's make this 200.
Mm-hmm.
This should be minus 100. You understand the idea here?
Yes, sir. Yeah. So
So
when we're writing like the delta H, we write all the in it. Wait.
wait.
Mm.
Easiest way is to understand this shit is to draw an energy profile diagram directly. So the idea here goes like this. We have this as the level for cyclohexane.
Mm.
Okay, it is more stable. So I'm going to be having something like this. Okay, let me just draw the full line there, that is easier. This is my level for cyclohexane. My benzene expected is at this level.
Yeah.
Expected. Right. So I had an expectation value of this much. This is my delta H expected.
Mm.
Okay. But my benzene in reality is not at that level. Benzene in real is more stable.
Yeah.
More stable means
Beneath.
less energy.
Yes.
So benzene
Below.
real is not there, it is here.
Mm.
So when I do the real energy level, experimentally when I do that, that comes out as this value, which is my delta H real, which is minus 200.
Mm.
So why is this difference coming here? Because benzene has resonance. This is my resonance energy.
Mm.
And because of resonance only, it is becoming more stable. Right?
Yeah.
So that's basically the idea here.
Okay.
You
Mm.
understand the principle here properly?
Yes, sir. Yeah.
So this is not just applicable for benzene. This is just a typical case for benzene, which I've taken and discussed. It applies in all other cases also.
Mm.
They can give you for other funny business also.
Yeah. Okay.
Clear properly?
Yes, sir.
So this is basically a few other definitions as well when it comes to what to say enthalpy changes. You have to practice questions. There is no shortcut. There are
No.
no shortcuts.
So,
You'll have
yeah.
to learn the hard way only. Um, ah, okay, I think we'll close it off today here.
Okay.
Any other doubts you have in atomic structure or any other questions you have in thermo now so far?
No, sir. No. Okay.
Sure.
Yeah.
Okay, we'll close off now then.
Yes, sir. Yeah. Sir,
Please
can you
practice.
send the notes?
Yes, I will
The
send
notes. Yeah.
this notes itself, no?
Yeah. The atomic structures.
Atomic structure also.
Yes, sir. Yeah.
Send both, yeah. Okay, all right, bye bye.
Yes. Yeah. Sir, you were saying something just now.
Huh?
You were saying something just now.
Prepare properly, don't waste the time
Oh, yes, sir. Yes.
because 30 questions is, yeah, you
Yes,
have
sir.
to be more efficient. 30 questions is spending too much time at this stage here, and time is unfortunately a commodity. And this is not a topic you're learning for the first time.
Yes,
Bye bye.
yes, sir. Thank you, sir. Have a nice day.